We sent a spacecraft to touch the sun, and it survived. What it discovered will change everything we thought we knew about our star. Right now, 93 million miles away, something extraordinary is happening. A human-made probe is diving through temperatures exceeding 3 million degrees Fahrenheit, traveling faster than any object we've ever built, 430,000 miles per hour. It's not just visiting the sun, it's penetrating its atmosphere, swimming through the same superheated plasma that powers all life on Earth. But here's what haunts scientists. The sun, our closest stellar neighbor, remains one of the universe's greatest enigmas. Light from its surface reaches your eyes in just 8 minutes. Yet after billions of years of shining down on us, we still can't explain some of its most fundamental behaviors. The Parker Solar Probe didn't just get close to the sun. It crossed a boundary no human technology had ever breached, the edge where our star's grip on reality itself begins to slip. And what it found there defies everything in our physics textbooks. Imagine standing next to a bonfire. The flames are hot, maybe 1,500 degrees. Now imagine the air 10 feet away from that fire being 10 times hotter than the flames themselves. Impossible, right? Heat doesn't work that way. It can't. Except on the sun, it does. The sun's visible surface, the photosphere, blazes at a relatively modest 10,000 degrees Fahrenheit. It's the temperature of molten iron, hot enough to vaporize any known material instantly. But venture just a few hundred miles upward into the corona, the sun's outer atmosphere, and something inexplicable occurs. The temperature doesn't drop. It skyrockets to nearly 2 million degrees Fahrenheit. This is the corona heating problem, and it's been tormenting astrophysicists for over 70 years. Every law of thermodynamics screams that this shouldn't happen. Energy flows from hot to cold, always. A heat source cannot warm something to temperatures greater than itself without an additional energy input. Yet the sun's atmosphere is somehow 200 times hotter than the surface below it. Think about that. The glass of a light bulb is hot to the touch. But what if the air surrounding it was hot enough to melt steel? That's essentially what's happening on the sun, on a scale that involves more energy than humanity has consumed in its entire existence every single second. Scientists have proposed theories: magnetic reconnection, wave heating, nanoflares. But theories aren't answers. They're educated guesses wrapped in mathematics. Until the Parker Solar Probe, we were trying to understand a furnace by standing in Antarctica and squinting really hard. The sun isn't just sitting there burning, it's hemorrhaging itself into space, bleeding plasma at a rate of over 1 million tons per second. This is the solar wind, a supersonic stream of charged particles that bathes every planet in our solar system. But here's where it gets genuinely strange. When these particles leave the sun's surface, they're traveling at a respectable 37,000 miles per hour. Fast, certainly, but by the time they reach Earth, 8 minutes later, they've accelerated to over 1.3 million miles per hour. They've gained more than 30 times their initial speed. Nothing we know should cause this. In space, there's no downhill, no gravity. Well, pulling these particles faster. Once they escape the sun's grip, they should coast, maybe slow down slightly due to interactions with interplanetary material. Instead, they accelerate violently. It's as if you rolled a ball down a hill, and halfway down, with no additional push, it suddenly accelerated beyond the speed you released it at. The physics simply doesn't add up. What's powering this acceleration? Some invisible hand pushing on every proton and electron? A cascade of energy transfer we haven't identified? Or is something fundamentally wrong with our understanding of plasma physics? The solar wind isn't just an academic curiosity. These charged particles slam into Earth's magnetic field, creating the auroras, those shimmering curtains of green and red light near the poles. But they also wreak havoc on satellites, disrupt GPS systems, and during severe solar storms, can damage power grids, plunging entire continents into darkness. Understanding the solar wind means protecting our technology, our civilization, But more than that, it means confronting a phenomenon that shouldn't exist. According to everything we thought we understood, getting to the sun is harder than reaching any other destination in our solar system. Far harder. In fact, it requires 55 times more energy than sending a spacecraft to Mars. This sounds backwards. The sun is right there, pulling everything toward it with immense gravitational force. Shouldn't falling into it be easy? Here's the problem. Earth isn't stationary. It's screaming around the sun at 67,000 miles per hour. When we launch a rocket from Earth, that rocket inherits Earth's orbital velocity. It's not just sitting at the starting line, it's already on a racetrack, going full speed. If you point that rocket straight at the sun, gravity will accelerate it. Yes, but the rocket's tremendous sideways velocity means it'll just swing past the sun in an elongated orbit, like a car drifting around a sharp turn at high speed. To actually reach the sun, you need to cancel out nearly all of that orbital speed. You need to hit the brakes hard. Doing that with rocket fuel alone would require a spacecraft the size of a skyscraper, with fuel tanks so massive, the payload would be microscopic. It's physically impractical. Enter the gravity assist, one of the most elegant tricks in orbital mechanics. Instead of fighting physics, you use it. The Parker Solar Probe performed a carefully choreographed dance with Venus, swinging past the planet multiple times. Each encounter slowed the probe down, shedding velocity like a car downshifting through curves. But there's a beautiful symmetry here. When the probe slows down, that energy doesn't disappear. It transfers to Venus, infinitesimally, speeding up the planet's orbit. The probe literally borrows speed from a planet to fall toward the sun. It's cosmic alchemy, trading momentum between worlds to reach the one place in the solar system that should be easiest to get to, but isn't. 7 Venus flybys. Years of patient orbital adjustments, all to shed enough speed to finally plunge into the star that gives us life. Every celestial body has a domain, a region where its influence dominates. For Earth, it's the magnetosphere, that protective bubble where our planet's magnetic field shields us from solar radiation. For the sun, that domain extends far beyond what you'd think. The sun doesn't have a solid surface. It's a roiling ball of plasma, with no clear edge where sun ends and space begins. But there is a boundary, invisible but critical. The end surface. This boundary marks the point where the sun loses its grip. Below it, magnetic field lines act like elastic bands, pulling solar material back toward the star. Plasma erupts outward, but snaps back, trapped in the sun's magnetic embrace. Above the end surface, the magnetic field can no longer hold on. The plasma breaks free, streaming into interplanetary space as solar wind. In April 2021, the Parker Solar Probe did something unprecedented. It crossed the end surface. For the first time in history, a human-made object entered the sun's atmosphere. How did scientists know? The particles told them. Normally, solar wind flows in one direction away from the sun, like water rushing downstream. But within the end surface, the flow is chaotic. Particles swirl, eddy, and sometimes flow backwards, pulled by magnetic field lines still tethered to the solar surface. The probe's instruments detected this reversal. Suddenly, particles weren't just rushing past, they were dancing, some moving toward the sun, others away, caught in the star's magnetic whirlpool. The images sent back revealed structures called streamers, tendrils of plasma flowing outward like hair in wind. But the end surface wasn't smooth. It rippled and undulated, with peaks and valleys, expanding and contracting like a breathing organism. We'd crossed into the sun, and the sun was stranger than anyone imagined. Deep within the sun's corona, the Parker Solar Probe encountered something nobody predicted: switchbacks. Imagine you're holding a compass, watching the needle point north. Suddenly, without warning, it flips and points south. Then, seconds later, it flips back. Now imagine this happening, not with the compass needle, but with the magnetic field of the sun itself, a field millions of miles across, carrying energy that could power human civilization for millennia. That's a switchback. These aren't gradual rotations. They're violent, rapid reversals of the magnetic field direction, lasting anywhere from a few seconds to several minutes. During a switchback, the entire local magnetic structure flips by 180 degrees, as if reality itself briefly inverted. What causes them? The leading theory involves the sun's convection, the churning of plasma from the interior to the surface, like boiling water in a pot. These convective cells create gaps and turbulence at the photosphere. Magnetic field lines, anchored in the roiling surface, twist and tangle. Sometimes they snap, reconnect, and whip outward in S-shaped curves. These curves are the switchback's magnetic field lines folded back on themselves, creating localized regions where particles suddenly flow in the opposite direction. But here's why this matters. Switchbacks may be the key to both the corona heating problem and the solar wind acceleration mystery. When magnetic field lines reconnect and snap, they release tremendous energy that could heat the corona. And these writhing magnetic structures could act like a whip, accelerating particles to the extreme speeds we observe. The Parker Solar Probe is still gathering data, still watching these switchbacks form and dissipate. We're tantalizingly close to solving two of the sun's greatest mysteries. The answers might be hidden in these violent magnetic reversals, these moments when the sun's own field ties itself in knots and then explosively unties them. Surrounding the sun is a cloud of dust, microscopic remnants of the solar system's formation, debris that never coalesced into planets. Theoretical calculations predicted that close to the sun, this dust couldn't survive. The intense radiation and heat would vaporize it, creating a dust-free zone. But theories aren't facts until you measure them. The Parker Solar Probe conducted time series observations as it spiraled inward. At about 6.2 million miles from the sun, the dust density began dropping. By 4 million miles, it reached the detection limit. The dust-free zone was real. Think about what this means. There's a sphere around the sun, millions of miles wide, where solid matter cannot exist. Anything that enters this zone, rock, ice, metal, is atomized, torn apart by photons, and swept away by solar wind. It's a boundary beyond which physical objects cease to be. Now consider this. The Parker Solar Probe ventures much closer than 4 million miles. It reaches perihelion at about 4 million miles from the sun's surface, well within this annihilation zone. So why doesn't it melt? The answer is engineering brilliance and a strange quirk of thermodynamics. The probe's heat shield is a marvel. It's 8 feet wide and 4 inches thick, made of carbon foam sandwiched between carbon composite plates, coated with white ceramic paint. That paint reflects sunlight. The foam, 95% hollow, barely conducts heat. When the shield faces the sun, its outer surface reaches 2,500 degrees Fahrenheit, hot enough to melt aluminum. But 4 inches away on the backside, just 570 degrees. That's cooler than a pizza oven. Behind the shield, water circulates through the spacecraft, drawing heat away from instruments and radiating it into the cooler darkness of space. Autonomous sensors ensure the probe always keeps the shield pointed sunward. Deviation means death. But here's the real trick. Temperature and heat aren't the same thing. The corona is 2 million degrees, yes, but it's also a near-perfect vacuum, millions of times less dense than Earth's atmosphere. Temperature measures the average energy of particles. Heat transfer depends on how many particles actually hit you. Put your hand in a 200-degree oven, and it takes a minute to feel pain because air molecules are sparse. Put your hand in 200-degree water, and you're burned instantly, because liquid water has far more molecules per cubic inch. The corona is hot, but nearly empty. The probe passes through millions of degrees, yet receives relatively little heat. It's the electromagnetic radiation from the sun itself, photons streaming directly from the photosphere, that poses the real danger. And that's what the shield blocks. The Parker Solar Probe exists in a realm where conventional intuitions about heat break down. It swims through hell and emerges unscathed, not because it's invulnerable, but because it understands the nature of the inferno. The Parker Solar Probe will continue its mission through 2025, making closer and closer approaches. Each orbit brings new data, new mysteries, new answers. The sun is revealing itself, layer by layer. But why does this matter? Why spend billions to study a star we see every day? Because the sun isn't just a ball of gas 93 million miles away. It's the engine of everything. Every breath you take, every calorie of food you consume, every watt of energy powering your screen right now, it all traces back to sunlight. The sun is the architect of climate, the sculptor of weather, the ultimate source of nearly all energy on Earth. But the sun is also dangerous. In 1859, the Carrington Event, a massive solar storm, struck Earth. Telegraph systems worldwide sparked and failed. Auroras were visible in the Caribbean. If that happened today, with our satellite networks, power grids, and GPS systems, the damage would be catastrophic. Trillions of dollars in losses. Communication systems down. Navigation crippled. Understanding the sun means protecting ourselves. The more we know about solar wind acceleration, coronal heating, and magnetic field behavior, the better we can predict solar storms and shield our technology. And there's more. The solar wind carries helium-3, a rare isotope that could fuel fusion reactors clean, nearly limitless energy. The moon's surface, bombarded by solar wind for billions of years, is rich with helium-3. Understanding solar wind means understanding a potential energy source that could revolutionize civilization. The sun is 4.6 billion years old. It will shine for another 5 billion years. In that time, it will transform, swell into a red giant, and eventually consume the inner planets, possibly including Earth. Our future is written in the sun's fate. But for now, in this moment, we're privileged to study it, to send our instruments into its atmosphere, to decode the mechanisms that power our existence. The Parker Solar Probe is still out there right now, diving closer to the sun than anything before it, collecting data, surviving the unsurvivable, answering questions we've asked for generations. And in doing so, it reminds us, the universe is not done surprising us. The things we think we understand often hold depths we haven't fathomed. And sometimes, to find the truth, you have to be willing to fly into the fire. If this journey into our star fascinated you, if you want to explore more mysteries of space, physics, and the universe we inhabit, then subscribe to BrightBoundX. Hit that like button to help others discover these cosmic revelations. Share this video with anyone who's ever looked up at the sun and wondered what secrets it holds. Because understanding the universe starts with curiosity, and curiosity starts with asking, what if we looked closer? Subscribe to BrightBoundX, where science meets wonder.